Welcome back. In time series, we often observe similarities between past and present values. That's because we encounter correlation within such data. By knowing the prices today, we can often make a rough prediction about prices tomorrow. So in this lecture, we are going to introduce such a model. The auto-regressive model, or AR model for short, relies on past period values and past periods only to predict current period values. It's a linear model, where current period values are a sum of past outcomes multiplied by a numeric factor. For instance, if we take x as a time series variable, then an example of an AR model would look something like this. X in period t equals some constant c plus a numeric coefficient phi times x in period t minus 1 plus epsilon t. Let's go over the different parts of this equation to make sure you understand the notation well. For starters, x, t minus 1, represents the values of x during the previous period. For instance, if t is the current period and we have weekly values, then t minus 1 would represent last week's value. The coefficient phi is any numeric constant by which we multiply the lagged variable. You can interpret it as the part of the previous value which remains in the future. It's good to note that these coefficients should always be between -1 and 1. Let me explain why. If the absolute value of the coefficient is greater than 1, then over time it would blow up immeasurably. This idea can seem confusing at first, so let's take a look at a mathematical example. Say we have a coefficient for phi equal to 1.3 and a time series with 1,000 observations. Then the value at period 2, x2, would equal 1.3 times x in period 1. Since x3 equals 1.3 times x2, we can substitute x2 and get 1.3 to the power of 2 times x1. Then, as the more periods accumulate, the more the coefficient increases. When we get to the 1,000th period, we would have x 1,000 equals 1.3 to the power of 999 times x1. This implies that the value keeps on increasing and ends up much higher than the initial one. Obviously, not a reliable way to predict the future. Okay, now the only part of the equation we need to break down is epsilon t. It's called the residual and represents the difference between our prediction for period t and the correct value. These are usually unpredictable differences because if there's a pattern, it will be captured in the other incumbents of the model. Now that we know what all the parts of the model represent, let's try to interpret it. According to the equation, values at a given period are equal to some portion of prices in the last period, plus some constant benchmark and unpredictable shocks. Fantastic. Before we go on, it is vital to understand that we don't just use any AR model on a given data set. We first need to determine how many lags to include in our analysis. For example, a time series about meteorological conditions wouldn't solely rely on the weather statistics a day ago. It's realistic to say it would use data from the last 7 days. Hence, the model should take into account values up to 7 periods back. From a mathematical point of view, a model using 2 lags would look as follows. X in period t equals some constant c plus a numeric coefficient phi 1 times x in period t minus 1 plus phi 2 times x in period t minus 2 plus epsilon t. As you can expect, a more complicated model would consist of even more lagged values, x in t minus n and their associated coefficients, phi. The more lags we include, the more complicated our model becomes. The more complicated the model, the more coefficients we have to determine, and as a result, the more likely it is that some of them would not be significant. Now, in general, a model which takes into account more data to make a prediction is usually better. However, if the coefficients are not significantly different from 0, they would have no effect on the predicted values, so it makes little sense to include them. To determine the correct number of lags we should incorporate in our model, we rely on the autocorrelation and partial autocorrelation functions. In the next lecture, we are going to examine market index prices and their respective ACF and PACF graphs. Thanks for watching. Hello again. In this lecture, we are going to observe the ACF and PACF of prices to determine the appropriate number of lags we need to incorporate into an AR model. Since we already examined the ACF and PACF of the S&P 500 when we introduced the two functions, we'd better work with the FTSE values this time around. Okay, let's get coding. We've already seen how to employ the plot ACF and plot PACF methods, but it's still a good idea to quickly reiterate. We introduced the Stats, Models, Graphics, TSA Plots library, which we imported as SGT, and called the appropriate method from it. We are starting with the ACF in this case, so we add plot ACF. Then, in the parenthesis, we refer to the time series we are analyzing, which happens to be DF, market value. We then assign values to several of the important arguments, like 0 and lags, before setting a title to the plot. We can also use the title method to name the plot, because it allows us to increase the font size and make it easier to read. To achieve this, we set the size parameter to some numeric value like 20. Great. Now we've already seen what the ACF looks like for the S&P, so we know how to interpret the graphs. We see a pretty similar graph, where all 40 lagged coefficients are significant and slowly declining. Furthermore, all of them are positive and between 0.9 and 1, which indicates that the effects barely deteriorate over time. These parallels suggest the two time series are similar in the way they behave and the way past values affect present ones. Generally, we prefer parsimonious models since they make for more reasonable predictors and prevent us from overfitting the data. The more lags we include, the better our model will fit the dataset we feed it. Now, the risk is that the coefficients might predict the dataset too well, which makes the model prone to mistakes when trying to forecast future values. Okay, we know that the ACF captures both direct and indirect effects a previous value has on the current one. Since we want to get the most efficient model, we only wish to include past lags, which have a direct, significant effect on the present. Hence, we should examine the PACF before constructing a model with 40 lagged coefficients. Let's call the plot PACF method from the SGT package and assign values to the most important arguments as we did in the previous section. We can also use the title method to name the plot. Then we can run the cell and interpret the results. Notice how we have coefficients of different size, coefficients that are negative, as well as coefficients which are not significant. This is vastly different from the ACF graph we just looked at. Now you can observe that coefficients from the 25th lag onwards are not significant, so we can just ignore them. To elaborate, since the coefficients will be extremely close to 0, we assume their impact on the model is minimal, so they're not relevant to us. Thus, our model must include less than 25 lags. Fantastic! Another observation is that values after the 22nd lag are negative. At first glance, this seems somewhat odd, but knowing the specifics of our data, we can find a reasonable explanation. Since the frequency of the data is in business days, and there are roughly 22 business days in a month, we can anticipate some cyclical changes every month. In other words, the values a month ago negatively affect the values today. In reality, we can see that these changes are vastly overshadowed by the ones occurring in later periods when it comes to impact, so we should not overanalyze their contribution. Please note that we won't be able to always spot such a convenient pattern in our data, so this short explanation only applies to the current data set. Okay, finally, we're certain that the value for our first lag is greatly significant, so we must include it in our model. Next time, we'll try starting with a model including only the first lag, see how it fits the data, and analyze its coefficients. Thanks for watching. Welcome back. In this lecture, we're going to see how to fit a time series into a simple autoregression model. To achieve this, we're going to use the Stats Models, TSA, ARIMA model library to import the ARMA method. We've imported packages before, so this shouldn't be that difficult for you. Simply type from, followed by the name of the package, and import ARMA. Now that that's taken care of, let's get coding. For starters, we need to store the values of the method to see how they fit the model. Hence, we must create a variable called model_AR because we are storing the specifics for this autoregressive model in it. Next, we should set it equal to the output of the ARMA method. Of course, we need to pass on several arguments so that Python knows what data we're using and what specific type of autoregressive model we're testing on. So the first argument we pass is the time series we want to model. In this case, that's the set containing FTSE prices we stored under the market value column in the data frame. Therefore, we write df market value within the parenthesis. Next, we need to define the specific model we wish to use. Since this is a simple autoregressive model, we need to set the order argument to 1, 0. The 1 here represents the number of past values we wish to incorporate into the model. The 0 represents the fact that we're not taking any of the residual values into consideration. We'll explain why the latter can also be important in the next section of the course. For now, all you need to know is that an order of 1, 0 is called a simple AR1 model. Fantastic! After defining the model, we need to see how it fits the data and what values it assigns to the constant c and the coefficient phi. To do so, we'll call the fit method on our newly created model AR. For convenience, we can name this variable results AR. Thus our code is results AR equals model AR dot fit. Running the cell will result in fitting the model, or in other words, finding the most appropriate coefficients. Let's examine what actually happened. To achieve this, we can create a summary of the results, conveniently supplied by the summary method. So we should write results_AR.summary. This table of abridged details about the model contains several important parts we'll be examining throughout this course. For now, let's only focus on the lower part, which contains the coefficients and their associated p-values. The first column contains all the variables the model estimates. In this case, we only have 2, const and AR L1 market value. Intuitively, the first one represents the constant c, and the coefficient column contains its supposed value. The other variable is phi1 from our theoretical model. This suggests that this is the coefficient for the autoregressive value from 1 lag ago for the associated time series. Now that that's clear, let's look at the numeric values more closely and explain what each column of the table represents. As we stated a moment ago, the coefficient column represents the numeric values associated with C and phi1 from the AR model we defined earlier in the section. The next column contains the standard errors. It's a measure of how far away, on average, the model's predictions are from the true values. Next is the Z column, which contains the associated test statistics for significance, with the p-values on its right. Since the p-values are 0 for both, we can safely conclude that the constant and the 1 lag value are both significantly different from 0. The last 2 columns represent the critical values for the 95% confidence interval. If 0 is not a part of it, we can confirm the coefficients are significant. Okay, we notice that phi is 0.9985, which is approximately 1. That's something which coincides with the information we got from the ACF and the PACF graphs. Now, since both coefficients are significantly different from zero, we can try fitting a more complex model for greater accuracy. In the next lecture, we're going to create such models with several lags and see how the predictions change. Thanks for watching. Welcome back. Last time we saw how to fit a simple autoregressive model to a dataset. Since both the constant and the coefficient for one period ago were significant, we want to test if a more complicated model will be a better estimator. In this lecture, we're going to learn how to fit an autoregressive model for as many lags as we want. We'll analyze each one individually and then use the log likelihood ratio test to determine whether a more complex model makes better predictions. Okay, now that we have our expectations set, let's get coding. We'll start by building an AR2 model. In case you need a hint, an AR2 model will determine prices today based on prices up to 2 periods ago. The code we're about to write is not much different from the one for the simple autoregressive model, so we can reuse most of it. In fact, we only need to alter the order argument from 1, 0 to 2, 0. Since we wish to compare various models later in the lecture, we're going to store the values for each one. Let's call this model variable model AR2 and its results AR2. Throughout the lesson, we'll keep assigning similar names based on the number of lags we use for each model. Now let's examine the summarized table. We can see there are now 3 variables in the first column, rather than the 2 we had before. In addition, the coefficients for phi 1 and the constant have changed. That's because some of the changes in prices can be justified by the prices 2 days ago. However, let's observe the p-values of each parameter. Notice how the p-value for the new parameter is 0.226. Since the value is greater than 0.05, we can reject the null hypothesis. This suggests that the coefficient for the second lag isn't significantly different from 0. Therefore, we assume it's equal to 0. In layman's terms, this means that the prices 2 days ago do not severely affect those of today. A possible explanation is that all the effects they have are captured in yesterday's price. Thus, adding additional information doesn't provide significant value. Now, before we reach any final conclusions, we should check the coefficients for the AR3 and AR4 models. Usually, the more lags we include, the better our predictions become. However, we run the risk of overfitting. Let's compute the summarized tables for those 2 models and then introduce the log likelihood test, which will tell us if the more complex models are worth using. Okay, we can start by fitting the AR3 model. We already did the same for the AR2 model in this lecture, so you should be able to replicate the code without much difficulty. Simply change the values of the order argument and then rename some of the variables storing the model and its results. See how the second period coefficient is now negative? This differs greatly from what we had previously. However, its p-value is still greater than 0.05, so we can't confidently say the parameter is significantly different from 0. Therefore, its sign is of little importance, since we will equate it to 0 if we decide to use this model. Do you notice how the log likelihood located in the top right of the table has increased? Since the absolute value has decreased, but we are dealing with negative numbers, the log likelihood has increased. As a general rule, we prefer models with a higher log likelihood, but lower information criterion. Since that happens to be the case, we need to use the log likelihood ratio test, or LLR test for short, to determine whether the 2 models are significantly different. For convenience, let's define a function for the log likelihood ratio test so we can reuse the code time and time again. We will name it LLR test for short. It's going to take 3 parameters: mod 1, mod 2, and df. Of course, the first 2 are short for the models we want to compare, and df, the degrees of freedom. We usually only compare models with a single difference in this department, so we're going to set the default value for df to be equal to 1. What we're going to do next is fit the two models and store their associated log likelihoods in the variables L1 and L2. To achieve this, we use the LLF attribute for each model. Then, we compute the test statistic for this test, which we will name LR. After computing this, we'll rely on the chi-squared method and pass the LR and degrees of freedom as parameters. The value we store from calling said method will be the p-value we wanted to find. Since we want to have a nice numeric representation of the p-value, we're going to round the result to 3 decimal places. We do so by calling the round method when storing the variable. We end the function by returning the variable storing the p-value result. Great! Now that we've defined the function, we can use it to compare the two models. After calling the LLR test, we see that the difference in log likelihood is significant. This suggests that we should opt for the more complicated model. Similarly, we get a significant difference in the log likelihoods if we run the test for the AR3 and AR4 models. We can repeat the same process of fitting a more complicated model and checking if it gives us distinguishably greater log likelihoods until we reach a model where it doesn't. Moreover, the said model should also have its last lag not be significantly different from 0. If we wish to examine the results of the model and the p-value simultaneously, we must use the print function. In such cases, it is a good idea to add some clarifying message to ensure we know which part of the output the p-value is. Of course, we do so by adding the text in quotation marks. Transforming the numbering value into a string, and concatenating them via summation. This all sounds overly confusing, but as you can see, the code is extremely simple. For homework, make sure to incrementally increase the complexity of the AR model by trying out AR5, 6, and 7. For my analysis prior to preparing this lecture, the first model where both conditions are satisfied is AR8. Let's see what its summarized table of results suggests and also what its LLR test p-value is. Okay, so after defining the AR7, we can just copy the code we used for the AR3 and make all the necessary adjustments. Those include altering the order and names of all important variables. Great job! We can see that the p-value for the 8th lag is indeed insignificant, and the LLR test p-value is 0.57. Both of those indicate that including prices from 8 periods ago does not improve our model in any notable way. That's why we stop with the AR7, even though it may contain some non-significant values. Since the simple AR model served as a good predictor, we should use the LLR test once again to make sure that adding 6 additional lags is worth it. Make sure to put the simpler model first, and also set the degrees of freedom to 6 by passing a value to the df argument. Not surprisingly, the complex model yields a significantly greater log likelihood, so we decide to stick with it. Now, some of the results we got seemed rather confusing. On the one hand, the AR1 model served as a better predictor than the AR2 model, but higher lag models outperformed it, even with several non-significant coefficients. All in all, it seemed that the more lags we introduce, the better our model becomes. This is often the case when using AR models to predict non-stationary data. To avoid such issues, we should use a stationary time series. In the next lecture, we're going to explore the main approach financial analysts take when examining non-stationary prices. Thanks for watching. Hello again. When we introduced AR models, we purposefully omitted to state that they model stationary processes best. Hence, if the data comes from a non-stationary process, then the AR family of models will do poorly in finding the true relationship between the data. Earlier, we saw that S&P prices resemble a random walk, but we never tested whether FTSE ones do as well. We can do this by calling the augmented Dickey-Fuller test and interpreting the results. We already learned how to do this, but let's quickly reiterate just in case. We call the A.D. Fuller method from the STS library and put the FTSE values as an argument. After running the cell, we see that the p-value equals 0.33, so we can't conclusively say the data comes from a stationary process. That's why we can assume it is extracted from a non-stationary process. This suggests that we shouldn't rely on AR models to make accurate forecasts. But what can we do in such cases? Well, our best bet is transforming the data set so that it fits the stationary assumptions. In finance, the common approach is to use returns instead of prices when measuring financial indices. For anybody unfamiliar with the term, returns express the percentage change between the values for 2 consecutive periods. As intuitive as it may seem to some of you, it's important to state that positive returns indicate an increase in the price, and negative ones showcase a decline. Thus, if investors forecast positive returns in the future, they prefer keeping the stocks as the price goes up. Conversely, if the predictions show negative returns, then the stock depreciates, and they would prefer to get rid of it, while it is still valuable. Enough theory for now. Let's see how we can create the returns out of prices. We need to take the value of a period t and subtract the value for period t-1 from it. Then, we'd have to divide that value by the value of the earlier period, t-1. And finally, multiply the result by a factor of 100 to get the percentage values. Lucky for us, Pandas provides a method we can use called PCT change. As the name suggests, it returns the percentage change between the current and prior element. We can pass a value to the periods argument to determine the distance in time between the periods we want to compare. The default value is 1, so we don't need to specify it in this particular case. We should note that Pandas returns the percentages expressed as real numbers. To clarify, the method uses 0.02 instead of 2%. To turn these values into the pure percentages we're used to, we can multiply the entire time series by 100. We do so by applying the MUL method, which is short for multiply. The value we put in parentheses is the factor by which we are multiplying the entire series. In our case, the factor equals 100. We can stack the two methods and simply add .MUL 100 at the end of the percent change line. Remember that we need to record these values in order to examine them later. Since it is easiest to just add them to the data frame, we can store them in a new column titled Returns. Of course, the name of the variable is completely up to you, but using clear and indicative names is a good practice. Great. Note that we'll have one return value fewer than the prices. That's because we won't have any returns for the first period. We can't have any increase or decrease from the previous value if there are no previous values. Makes sense, right? Having missing values means there will be no way to find the correlation between the first and any other period. This will cause the autocorrelation function's failure to generate any coefficients. To avoid such issues, we simply remove the first period prices. Since we have several thousand observations, doing so should not significantly affect our data. We can overwrite these values by calling the iloc method into the data frame and typing 1, followed by a colon between the brackets. This means the new data frame would have all the elements of the old one starting from the second period. This is due to numbering in coding language starting from 0 rather than 1. So the row with index 1 is actually not the first one. Right. To make sure the returns don't come from a stationary process, we need to run the augmented Dickey-Fuller test once again. The code necessary to achieve this is essentially the same one we used for FTSE prices, but this time we'll pass the new time series as an argument. Fantastic. The test statistic falls far to the left of even the 1% critical value, which we see below as well. Thus, we can confidently state that the data comes from a stationary process. This is exactly what we were aiming for when switching from prices to returns. Marvelous work, everyone. Now we have a good understanding of why we use returns and how to compute them. So let's turn our attention to their ACF and PACF plots as we try to model the newly created time series. Thanks for watching. Welcome back. In this lesson, we're going to find and interpret the autocorrelation and partial autocorrelation functions of the returns on FTSE values. Since we've already seen how to compute these plots, we can directly start interpreting the results. Let's begin with the ACF. The plot greatly differs from what we saw with prices. For starters, not all coefficients are positive or significant. Additionally, values greatly vary in magnitude, instead of all being close to 1. By the looks of it, the first several lags are of great importance, since they are significant, but their coefficients are negative. That points to a trend where consecutive values move in different directions. This suggests that returns over the entire week are relevant to those of the current one. Since the relationship is negative, we can interpret this as some form of natural adjustment occurring in the market. Before we make any final decisions on what model we want to implement, let's first look at the partial autocorrelation function. Just as was the case for the ACF, we have already shown how to plot this for prices, so we only need to adjust the time series we are using. Okay, the results look uncannily similar to those we got for the ACF. One way to interpret this is that prices today often move in the opposite direction of prices yesterday. Hence, we tend to get price increases following price decreases, which falls in line with our expectation of cyclical changes. Intuition dictates that the further back we go, the less relevant the coefficient values should be. That's because the majority of effects they have on current values should already be accounted for due to the recursive nature of autoregressive models. Okay, we are now ready to explore how a simple AR model performs when predicting returns. Thanks for watching. Hello again. In this lecture, we're going to see how well a simple autoregressive model can be used to predict FTSE returns. To avoid any confusion, we should model returns in a separate file, so now is a good time to open up a new notebook. Remember to import all relevant libraries and functions, as well as all the necessary pre-processing code. You can always copy the code you already have to avoid typing it out all over again. After setting everything up, we need to define the model specifications. Then, once we fit the data, we can extract the results. I'm pretty sure you're already familiar with how it's done, so let's get right into coding. We start by creating a variable to contain the model. Since we wish to distinguish it from the one containing price specifications, we're going to add ret to the name. Of course, ret is just short for returns. We don't want to make our variable names too long, right? So we start with model ret AR. Then we set it equal to the ARMA method. We are using returns, which means we should put df returns in the parenthesis. The last step is to pass values to the order parameter. Great. Now that we have specified the model, we need to see how it fits the data. To do so, we use the method of the same name and record the results. Finally, we summarize the statistics of said results and examine the table on the screen. What immediately captures our attention is that the p-values of both parameters are over 0.05. This means that neither is significantly different from 0, so this model holds no real predictive power. This can be explained by the impact past values can have on yesterday's prices. The more easily yesterday's price is affected by higher lags, the more inaccurate its coefficient becomes. This is because of the accumulated compounding effects of lagged coefficients. Of course, this directly decreases the predictive power of the model. Therefore, we should proceed by testing whether a higher lag model serves as a better predictor. Thanks for watching. Hello again. Last time we saw how a simple AR model predicts price returns. In this lecture, we're going to test whether more complicated ones do a better job. Let's get started. We're going to begin by fitting an AR2 model, analyzing its coefficients, and then running the log likelihood ratio test. Once again, code-wise, we only need to alter the values of the order argument and the names of the variables. After changing everything accordingly, we can run the cell and examine the summary table. We can see immediately that the p-value for the second lag is 0. This means that phi 2 is significantly different from 0 and should be included in the model. Also, the p-value for the first period has decreased further. Maybe if we add more lags, it will actually become significant. Since the p-value for the new coefficient is 0, we suspect that the change in log likelihood is also significant. To be completely certain, we still run the LLR test for the AR1 and AR2 models. Make sure to put the simpler model first and the more complicated one second when calling the function. We get a p-value of less than 1%, which supports the claim that this model is a better fit than the previous one. Also, we can notice that all three ICs, or information criterion, are lower than they were for the AR1 model. Great job! What about an AR3 model? First, we must set the model specifics and fit it to the data. Then, summarize the results and print the table on the screen. Once again, we should set our focus to the p-values of the parameters. This time, all of the coefficients related to past values are significant at the 5% level. Since the p-value for the newest lag is 0 yet again, we expect the LLR test to suggest that this model is better than the previous one. To avoid any uncalled errors, we should run the test anyway. As expected, we get a very small number, 0, so the two log likelihoods are distinctly different. Okay, what we see next is that the information criteria are lower once again, so we can safely assume this model outperforms its simpler counterpart. As you've probably assumed by now, we must repeat the same several steps until we reach a model where the additional coefficient is insignificant. The LLR test fails, and we get higher AIC or BIC values. For returns, this occurs when fitting the AR7 model. Since it fails on every aspect when comparing it with the AR6, we opt for the simpler model. Fantastic work! Modeling prices and returns for a single market is extremely useful. But if we wish to compare how different ones perform, we should account for the varying magnitude between countries. In the next lecture, we are going to explore the process of normalizing a dataset. Thanks for watching. Hello again. We mentioned that we prefer relying on returns rather than prices when using AR models. This is because of the non-stationary nature of prices. Normalization can mean several different things, but in the case of time series, when we normalize a set of values, we basically map every value of the sample space to the percentage of the first value of the set. The resulting series is much easier to compare with other time series. In general, by normalizing two time series, we can compare how well they perform relative to one another. This gives us a better understanding of which ones to invest in and which ones to avoid. For instance, a flat increase of $100 in the price of the S&P will be a much more significant change than the same absolute increase in the price of the Nikkei, since Nikkei prices are usually several times higher. However, an increase in the price for S&P equivalent to 5% of the original value is comparable to the same percentage increase for the Nikkei. Let's see how we compute these normalized prices. For starters, we need to set some benchmark. This value should be used as the central piece we use to compare all subsequent values of the time series. We could pick any date within our data set, but the interpretation seems easiest if we simply go with the value for the first period. To extract said value from the data frame, we can use the ILOC method. Since the first element is the one with an index of 0, then we simply write DF market value ILOC 0. We plan on using this value going forward. That's why we're going to assign it to a variable. For convenience, we can simply call it a benchmark. Next, we need to divide all the values in the set by this number. So we apply the div method and put the variable in parentheses. We also multiply by a factor of 100 because we prefer working with percentages. For convenience, we can stack these methods one after the other, so we add MUL 100 to the line of code. Perfect. As we've mentioned several times over, AR models work best with stationary data, so we need to run the augmented Dickey-Fuller test before we are certain the values are useful. Let's call the AD Fuller method from the STS library and interpret the p-value. As was the case with non-normalized prices, we can see that the test yields a high p-value, which suggests non-stationarity. Thus, normalizing prices did not result in stationary data. Therefore, we will not be able to use an AR model with the normalized prices. However, normalization is still a great practice for comparing time series. Let's go a step further and normalize the returns instead. Suppose, historically, the S&P provides significantly higher returns than Nikkei. For instance, Nikkei yields a steady 2% increase over a given period, while the S&P returns an average 3% in the same time span. Then if returns for both are around the 3% mark for the period we are observing, Nikkei is significantly outperforming its expectations. So to avoid any biased comparison when analyzing the two sets, we often rely on normalized returns. They account for the absolute profitability of the investment, in contrast to prices. Plus, they allow us to compare the relative profitability as opposed to non-normalized returns. Overall, they are much more reliable measurements than the other two. To generate these normalized returns, we retrace our steps back to when we did the same for prices, but use the return series we generated earlier. Thus, we compute the benchmark using the ILOC method. Then divide by the outcome and convert into percentages by multiplying by a factor of 100. Great job! Now, once again, let's test if the data comes from a stationary process. Since the series was derived from the returns set, which was also stationary, we suspect the Dickey-Fuller test will suggest stationarity once again. Even though we only changed the magnitude of the data after normalizing, we should always double-check and actually run the test. As was the case with non-normalized returns, the test statistic is significantly smaller than the 1% critical value of negative 3.43 shown below. Therefore, we can say with great certainty that this data is stationary. Furthermore, we can conclude that normalizing does not affect stationarity. Well done! We're going to analyze normalized returns and non-normalized returns. This should provide us with enough understanding of why one is much more preferred than the other. Thanks for watching. Welcome back. We've already gone through the process of fitting different lagged models for both prices and non-normalized returns, so we're going to take the exact same course of action. In this lecture, we're going to start by fitting a simple autoregressive model for the normalized returns and build up until we find one that describes the data best. Let's begin. We start, once again, by fitting the simple autoregressive model and examining the table. The p-values are both greater than 0.1, so we can't be conclusively certain they are non-zero. Do you recall that we had observed something very similar for non-normalized returns? Before we move on to more complicated models, let's observe the summarized table for non-normalized returns once again. We can notice that all the values for phi1 are absolutely identical between the two tables. If this persists, we can safely assume that normalizing does not have any effect on model selection. To be on the safe side, let's fit an AR2 model and compare the outcomes to the AR2 results for non-normalized returns. We know how to do both by now, so you can copy the code we've used and make the necessary changes. After doing so and displaying the two summarized tables, we find the exact same trend. Normalizing the values only had an impact on the constant, but not on any of the lagged coefficients. Therefore, we can suspect that the same model that failed for regular returns would also fail normalized returns. Let's just check how well the AR7 predicts normalized returns. You already know what changes need to be made to the code. We see the exact same pattern as before, so we should stick with the AR6 model. This means using normalized values has no impact on model selection. Perfect! With regard to the theory we've been through so far, we still haven't explored the errors. They will indicate to us if we are omitting any major trends in the data. Thanks for watching. Hello again. In this lecture, we are going to extract the residuals for all the models we believe to be good fits. Then we'll examine a summary of their statistics before testing them for stationarity. Ideally, the residuals should follow a random walk process, so they should be stationary. Finally, we are going to apply the Dickey-Fuller test before plotting the values. Make sure to use the appropriate notebook, since the newly created returns file will not contain the variables storing the correct models for prices. To extract the residuals of the results of a model, we need to simply call the resid argument. Now, since we want to associate the residual for each time period, we're going to add a new column to our dataset and call it res price, which will contain the errors for prices. Previously, we decided that the AR7 model was the best fit for prices, so we must use the model AR7 variable. Since we need to extract this from the results, we should fit the data first and then select the resid argument. Alternatively, we could also use the results of the model since we already stored them. To get a general feel of the data, we can use the mean and var method to find the expected value and variance of the distribution of the residuals. The mean is close to 0, which suggests that, on average, our model performs well. But the high variance indicates the residuals are not concentrated around the mean of 0, but are all over the place. This is primarily because AR models perform poorly when predicting non-stationary data. Now, we still need to run the Dickey-Fuller test to see if the time series is stationary. We call the AD-Fuller method from the STS package and use the newly generated time series as an argument. After running the cell, we get a p-value equal to 0. This suggests stationarity, so the error terms fit our expectations so far. Do you recall that the coefficients for the autocorrelation function of white noise should all be 0? To make sure the errors of our predictions are random, we should examine the ACF of the residual values. The good news is we're already familiar with the plot ACF method and the arguments we need to provide it with. Just make sure you remember to add an appropriate title to the plot and set the font size. After plotting the function, we can see that the majority of coefficients fall within the blue region. As you know, this suggests they are not significantly different from 0, which fits the characteristics of white noise. However, the few points that fall outside this area lead us to believe that there's an even better predictor. Next, we must plot the values of the residuals to see if they resemble what we are used to expecting from white noise data. We do so by calling the plot method onto the new time series. The graph looks nothing like the original ones we had for prices. We cannot find any obvious pattern for the data, so our choice of model seems correct. It's important to note that since we used an AR model on non-stationary data, our predictions might still be far from great. Alright, now we're going to repeat our actions for the residuals of returns. Make sure to use the appropriate notebook. Once again, we add a column to our existing data frame by taking the resid attribute. The only difference is that this time we use the associated model for returns rather than prices. It's crucial to remember that we decided that AR6 rather than AR7 was the suitable choice for price returns. Next, we find the mean and variance once again. And their values are closer to what we might expect from white noise data. A mean extremely close to 0 and a variance of around 1 indicate that our choice of model was pretty good. Running the Dickey-Fuller test returns values close to those of the price residuals, so we have confirmation that the data is stationary. Since white noise is stationary, this is exactly what we wanted. As we just saw, the next step is to compute the ACF and examine the coefficients. Of course, we can just copy the code we ran earlier and only change the time series from df res price to df res ret. Splendid! We can observe a very similar scenario where most but not all coefficients are not significant. Hence, our model is a good predictor, but we have a good reason to believe a better one exists. Finally, we plot the data. As was the case with prices, our residuals are mostly low, except for around the end of 2008. This, of course, coincides with the start of the Great Recession, which few people could have anticipated. However, analysts have adapted to account for such unpredictable events. So in the next lecture, we are going to expand our modeling skills with this idea. Thanks for watching. Welcome back. Last time we ended by mentioning unpredictable events and how we can handle them. In this lecture, we're going to introduce the idea of learning from our mistakes. Let's get started. So an autoregressive model needs time to adjust from a big unexpected shock because it often relies on the past data, regardless of how close its predictions were. However, there exists a type of self-correcting model which takes into account past residuals. Such models adjust to unexpected shocks more quickly because the predictions are corrected immediately following a big error. The more errors we examine, the more adapted our model is to handle unforeseen errors. These types are known as moving average, or MA models, because absorbing these shocks allows the mean to move accordingly. They do exceptionally well at predicting random walk datasets because they always adjust from the error of the previous period. This gives the model prediction a much greater chance to move in a similar direction to the values it is trying to predict. It also stops the model from greatly diverging, which is incredibly useful for non-stationary data. We will talk more about the mathematics of these models and how to implement them in the next section of the course. See you all there, and thanks for watching.